All right. Well, good morning or good afternoon, depending on your location. It's my pleasure to welcome you to the AIPG Lunch and Earn webinar for August. I'm Aaron Johnson, Executive Director of AIPG, and today I also happen to be the presenter. Before I get started, a couple of quick things. If you need a certificate of participation, that will be sent to the email you used to register for the webinar, so check your email for that. If you don't see that within the first 24 hours or so, reach back out to us and we'll ensure that you get that certificate. If you're taking this webinar to receive continuing education credit for your New York State registration, the New York State Education Department requires that those people who look for continuing education for New York take an assessment as part of any continuing education event. That's a 5-question quiz that will show up as a link in the chat toward the end of the webinar. You have to answer 4 of those 5 questions right to get your continuing education credit, and you can take that quiz as many times as you like. So please be aware of that if you're in New York State. Well, since I usually do the introductions, I'll introduce myself today. For those of you that don't know me, my name is Aaron Johnson. I'm the Executive Director of AIPG. I have a PhD in economic geology and geochemistry from the University of Missouri. I spent about 15 years as a college professor. I've also done some consulting work on Mississippi Valley type ore deposits. And right now, as part of my work with AIPG, I work with the United Nations Economic Commission on Europe as part of their framework classification initiative. That initiative seeks to find ways to classify natural resources and their development pipeline, so where they are in terms of being able to bring natural resources to market. I work in the minerals group and in the professional development group. So that's kind of my background. Today I'm going to, I think, try to make the case that copper may be the most critical of the critical minerals, at least in the shorter term, say in the next 25 years or so. And we'll see if I'm successful making that case. Toward the end, if you have questions, you can feel free to drop those in the chat and we'll have a little Q&A at the end. I'm going to talk a little bit about historical use of copper, make the case that copper has been critical for maybe 10,000 years. We'll talk a little bit about geochemistry of copper, kind of where we find it and how abundant it is. A little bit of mineralogy, because some of you may have slept a few days since you last had a mineralogy class. We'll talk about the major copper deposit types. And then we'll get into sort of trends in copper production along with projections for future needs, and finish up talking about the response to this increasing demand and make maybe a few generalized conclusions. I also want to give the caveat that I'm not a copper mining expert. So if you have expertise in these deposits, first, we'd love to have you come talk about porphyry copper or skarn-hosted deposits. But the information I'm going to give is going to be at that 10,000 foot level. So I'm not going to go into great detail. I'm going to try to summarize a deposit type in a slide or maybe 2, and where we know that for these individual deposit types, you could give an entire class just on one type. So really a generalized overview when it comes to the individual deposits. All right, so historically, when I dug into this, I was kind of surprised at just how far back human copper use goes. The oldest documented copper object where we know that humans modified it for human use dates back over 10,000 years. It's a pendant that was found in Iraq. And early on, the uses for copper appear to be primarily decorative, but humans very quickly started making copper tools. Those tools included things like fish hooks, projectile point axes, knives. In the United States, the early copper culture, which is kind of centered in Wisconsin and northern Michigan, left behind a trove of objects that date to about anywhere from 4,500 to 6,500 BC. That's not really a surprise because up on the Upper Peninsula of Michigan is the Keweenaw Peninsula, which is host to large native copper deposits. People were smart. If you've ever been up there and you've done any collecting in that area, you know, the copper occurs as fine wires and little thin sheets, and it's pretty easy to cut yourself on those sharp pieces of copper. So you could see how native people could easily have seen that and jumped from I cut myself to this would be a really good tool. This is an example of one of those tools from up in the early copper culture. It's about a 6,500-year-old spear point made of copper. It was found in Wisconsin. By about 5000 BC, so about 7,000 years ago, we see the first unequivocal evidence of extraction of copper using heat processes. This happened in Serbia and in Hungary, and we see fairly widespread evidence of leftover copper slag from heating and processing copper ore. This is what that looks like, and you can see sort of this green residue is probably some leftover copper that wasn't fully extracted from the heating and processing of that copper ore. 3500 BCE, so about 5,500 years ago, we start to see bronze. That's an alloy of copper and tin. The origin of bronze is interesting. No one's absolutely certain how it might have originated, but one of the thought processes is that it was an accidental mixing, kind of a Reese's peanut butter cup, you got your chocolate on my peanut butter moment, when someone accidentally mixed copper and tin and they found that what came out of it was maybe even better than what went in. Within a couple thousand years, we're making weapons and armor from bronze. Bronze is harder, it holds an edge longer. So there were some definite advantages to bronze armor and weaponry. Here's an example of an Illyrian bronze helmet. This is from the Metropolitan Museum of Art up in New York. So fairly typical of some of the bronze work that we were seeing 1600 BC, so 3600 years ago. It became really interesting when the Shang Dynasty in China started adding lead to bronze. Also, this probably was intentional. Probably wasn't an accident that lead was added. What happened was it lowered the melting point of bronze and it made the molten material flow a little more easily, so it allowed for more bronze casting to take place. Different shapes, more designs, and the ability to then cast bronze into other uses. So that was a really big advancement. So for at least probably 7,000 years up to 1600 BCE, humans had been relying on copper and copper alloys in more and more extensive applications. Just a few hundred years after the introduction of bronze, brass was discovered, and initially brass was a little more difficult to find applications. Wasn't quite as hard, but it was a lot more decorative. So we start seeing brass used in a decorative sense, and now copper use expands. It goes beyond tools, goes into jewelry and decorative use on buildings. So the use of copper really becomes extensive, starting about 3500 BCE and really moving to the present. By the Justinian era, the Justinian Academy was founded in 529 BC in Greece. The Greeks really started to use brass with bronze for a lot of the ornamentation on buildings, statues, or works of art. And then in Rome, when Augustus implemented what's called the Augustan reforms, that was about 20 years after Julius Caesar was murdered on the floor of the Senate. The Augustan reforms required the use of brass for coins. So at that point, the use of copper for monies and became even more extensive. This is a photograph I stole off of eBay. Somebody that's got a Augustan coin for sale that's up for auction. You can actually see Augustus spelled out here, Augustus. And those would be brass coins that were for use in early Roman Empire, so after the fall of the Republic and the beginning of Imperial Rome. The next really big step for the use of bronze especially came during the Yuan dynasty. That's 13th century China. And by the 15th century, the use of bronze for firearms had really expanded. This is a photograph of a bronze hand cannon. So this would have been held in your hand, would have been packed with, just like any other cannon, powder, wadding, and a projectile, and then ignited. And that hand cannon allows you to shoot that. If you've got kids that have ever played any of the civilization-based games, things like Civ 4 by Sid Meier or the Age of Empires games, which is what my son played, the hand cannoneers, as they're called, become an important advancement in the use of weaponry. This is a bombard mortar, so a much larger mortar that was used with a large cannonball during siege weaponry. That's a bit later, a couple hundred years after the first hand cannons. But it shows the extent to which, again, copper and copper alloys now are becoming ubiquitous through human civilization. Copper cookware shows up in the 17th century. So the 1600s, Paul Revere, our midnight rite of Paul Revere fame, was a silversmith and also a coppersmith. So if you've seen Revere ware for sale, that is named for Revere, and he was a tinkerer, a potter. One of the more interesting applications that I found as I really kind of dug through this was the use of copper sheathing to protect wooden ships from boring organisms. I've got a photograph here of old Ironsides. That's the USS Constitution. Copper sheathing being replaced in 2016. And what I thought was interesting is I also dug into modern wood treatment. So if you look at the treated wood that you put on your decks, especially growing up where I did down in the lower Midwest, down in Missouri, a lot of those are copper compounds. And it really made me wonder if the sheathing worked not necessarily because it kept the wood-boring organisms from being able to get to the wood, but if when that copper interacted with seawater, it created some of those copper compounds that then got infused to the wood and acted as, for lack of a better word, a pesticide. Of course, copper plumbing and wiring become ubiquitous by the 19th century. And in the 20th century, we see widespread use in electronics and more than now 400 different copper alloys that incorporate a broad variety of elements, copper alloyed with aluminum, beryllium, silicon, nickel, manganese, and iron, in addition to some of these traditional alloys. And what that means is that in a given day, if you think about what you interact with today, it is nearly impossible to be a member of human society and not depend on copper in some way, from power transmission, copper wiring in our walls, we've got copper in our cell phones, computers, laptops, automobiles, power grid. Modern society really relies on copper to function, and it's reflected in demand. According to the USGS, as of January 2025, projected demand for this year is 28 million metric tons globally, 28 million metric tons of refined copper. Now, to put that in perspective, over the course of the 20th century, only about 400 million tons of refined copper was produced in that 100-year period. So we're talking about a tremendous demand for copper just in the coming years, but especially just this year, 28 million metric tons. So geochemically, copper is in the transition metals. It's element number 29. The atomic weight 63 grams per mole. You can look that up. What's interesting is that it tends to form either +1 or +2 ions. And it tends to be of the correct size to go to a lot of the same places where you'll see calcium or nickel or potassium. It's kind of got the right size and charge density to hang out with some of those same chemical species. When I used to teach, I used to tell students that when we think geochemically, we want to know what copper is, where does it hang out, and who are its friends, right? Who does it hang out with? So we can kind of trace where copper will go by thinking about ions that are similar charge and similar size. What that means is that copper is going to want to form oxides and sulfides and hydroxides and carbonates and even some sulfates. So we would expect to see copper in those same kinds of geochemical locations or geochemical environments. There are two stable isotopes. We're not going to talk about that too much, but if you're in exploration, you may very well use the stable isotopes of copper to build some exploration models, especially if you're thinking about where that copper originates and the pathways it takes to get from source to depositional environment when you're making an ore deposit. There are a lot of radioisotopes. We won't talk about those necessarily either, but we can create those and they have fairly short half-lives, so we can use those for medical imaging purposes. In terms of crustal abundance, copper is about 60 parts per million in the crust. So if we go to anywhere in Earth's crust, we may find that we're going to find on average 60 ppm of copper. We look at cutoff grades, though, our cutoff grades are significantly higher. Now, these are typical grades. They're not absolutes. If you get the right deposit and the right overhead, you may have your open pit cutoff grade be less than 0.2%, or it could be a little higher. But what I really want to get at here is the amount of concentration that it takes to make an ore deposit when you've got a background rate of 60 ppm. So for open pit mining, you're looking at concentrating copper somewhere between 30 and maybe 85 times background levels. To be able to mine underground, maybe go from 80 to closer to 170 times the background level. So it takes a unique geological environment if you're going to make a copper deposit. Not unique, it takes a specific uh, geochemical environment to make a copper deposit. One of the things that really helps us out is that copper and chloride get along really well. And if you're not familiar with complexing, chloride likes to hang out with metal ions. It'll hang out with lead and zinc and copper. And what it will do is it'll make a soluble complex that you can have copper bond to a couple of chloride ions, or maybe three or maybe four. And then that makes copper soluble in water. And that means that hydrothermal fluids are going to be important. The analogy that I give, my wife absolutely loves dogs. She's never seen a dog she doesn't like. And when we go out and we go out for the afternoon and we go to Home Depot or we stop somewhere, every once in a while, the ASPCA or one of the local shelters will be there with their rescue pets. And it is my job to shield her from dogs. Because if I don't shield her from dogs, they come home with us. Because Maureen is really attracted to puppies. Copper is really attracted to sulfur, and it's attracted to oxygen, and it's attracted to sulfate and carbonate. But the chloride ions, they're the bodyguards. They do my job. They keep copper from seeing that sulfur is available, and that allows the copper to travel. Now, at some point, the chloride has to get knocked off the copper. Maybe we change temperature, maybe we introduce a competitor. If I'm at Home Depot and I run into a friend of mine and I get distracted, all of a sudden Maureen's over there adopting a dog because I went somewhere else. So in our geochemical analogy, we just need to destabilize those complexes. And if we've got some sulfur or we've got some oxygen or we've got some carbonate around, we can make copper minerals precipitate out. And if we can make that stable, that environment stable, and keep bringing copper in, we can really concentrate copper above that background level. Our ore minerals, pretty straightforward. Native copper. We love native copper. When we can find it, it's 100% copper. We don't have to do anything other than pulverize it out of the rock and try to separate it. One of the best known environments is up on the Keweenaw Peninsula in Michigan. And if you happen to be an expert on the Keweenaw Peninsula and Michigan copper, we would love to have you come and give a lunch and earn. So if that happens to be you and you're interested, reach out to me. Yes, that's a shameless plug. So please let me know. Sulfides, chalcopyrite, chalcocite, covellite. We'll talk a little bit about chemical formulas and percent copper in these. So I'm really not going to give you formulas here. We'll talk about that in just a minute. I will say that chalcopyrite tends to be the most commonly utilized copper sulfide ore mineral, although it's not necessarily the most desirable. We see a lot of oxides and hydroxides and carbonates, cuprite, malachite, and azurite. Malachite and azurite, of course, most folks are familiar with that. Those are the brilliant blue and green minerals that we see associated with places like the Copper Queen down in Bisbee. You'll note that we don't see copper silicates in the list of copper ore minerals. And it's because processing silicates, first off, they have less copper in terms of weight percent from the mineral. And second, it takes a lot more energy to process copper out of a silicate, break those silicate bonds, which tend to be stronger and they tend to be more covalent and less ionic. So it becomes more difficult to pull copper out of those silicates. This table just shows the formulas and the names of the minerals. We're not going to quiz you over that. So if you're worried about taking this quiz at the end, I'm not going to ask you for the weight percent copper and chalcopyrite. That's not the kind of question that we really want to focus on. But I do want to note that I've listed these in order of the weight percent copper within the mineral. So chalcopyrite tends to be probably the most abundant. It also has the lowest copper percentage. Now, it's not a surprise that it's abundant, right? Iron's pretty abundant, and you only need one iron mineral or one iron atom and one copper atom and a couple of sulfides to make chalcopyrite. Look, we'd love to have bornite. It's got a lot more copper in it, but when you've got to take 5 copper ions and one iron ion and then add them to sulfur, it's a little harder to do that. The solution has to be a lot more copper rich if you're going to make bornite rather than chalcopyrite. So just looking at these, I mean, the idea here is that these are all pretty high in terms of their copper content. 34% copper by weight is still a pretty good number. And if you can find 800,000 pounds of that stuff, you're going to take home a pretty big payday if you're mining underground for it. Occurrence of copper is really interesting. One of the things that I know about copper is we've really been mining copper hard since about 1905 or so. That's when we really started going after copper significantly. The sort of the steam powered dragline was invented in about 1898, and that revolutionized copper mining. It allowed us to go after lower weight percent copper deposits. And since that time, copper deposits have been studied extensively, and you could do a series of talks just on copper deposits. So this is really the 10,000-foot overview. The first thing to note about all of this is hydrothermal fluids are the key. And in almost every copper deposit, not everyone, but in almost every copper deposit, hydrothermal fluids have a role to play, almost always transporting that copper as some sort of chloride complex. The probably most abundant in terms of the sheer number of deposits are porphyry copper deposits. They're named because they're associated with porphyritic igneous intrusions. Skarn deposits, so named because they're contact metamorphic deposits. Volcanogenic massive sulfide deposits, or VMS deposits. These are associated with volcanism, typically underwater, but not always. And then sediment-hosted deposits like those of the Kupferschiefer, which literally means copper shale, or the Central African Copper Belt, either of those being large sediment-hosted deposits, but again, deposited most likely by hydrothermal fluids. And then finally, there are a couple of Mississippi Valley type deposits, although generally that's a secondary ore, but they can be significant, sometimes 1 or even 2% copper, and in some cases a fair amount more than that if the situation is a bit unique. And we may talk about that just a little bit as well. Porphyry copper deposits. They're large, they're widely distributed, often with subduction zone volcanism, although not always. They depend on porphyritic intrusions, often of intermediate to felsic composition. In 1970, two economic geologists named Lowell and Gilbert built a model that showed that copper enrichment was associated with specific types of alteration. They identified alteration zones and then used those zones to map where the highest grade copper could be found. And it's a model that works the vast majority of the time and gives us a really great prospecting model. If we think we found a porphyry deposit, if we can identify those alteration zones, we can start to hone in on the higher grade sections of the deposit for mining purposes. There are two primary types. There's some that bear molybdenum and some that bear copper. I actually was lucky enough to go to the Silver Bell mine just outside Tucson. This, if you can see it, is a sample of ore from Silver Bell. This little bit of green right in here is malachite, and then back over here, the blue is azurite. Those are copper carbonates. Silver Bell does, however, also host molybdenum, and I've got a sample of the molybdenum ore as well from Silver Bell. You can see that this gray material is actually molybdenum sulfide. So Silver Bell produces both, right? It is molybdenum bearing, but still copper dominated. Deposition is by the circulation of hydrothermal fluids as a result of the heat associated with intrusion. And when these deposits are closer to the surface, oxidizing, sometimes groundwater, sometimes deeper groundwater, I'm not sure it would be something you would think of that you could pull out of the ground and utilize, but oxidizing fluids can then create copper oxides and copper carbonates at the top. And the miners often refer to that as a leached cap. In the United States, we've got a number of these deposits in Arizona, New Mexico, and Utah that are associated with basin and range extension. The Andean deposits in Chile account for 25% of global copper production as of 2025. Peru accounts for another 16%. So just those two locations, the porphyry copper, over 40% of global production from those two countries. This is the model. I'm not going to beat a dead horse here. On the left, it shows the alteration zones and types of alteration. On the right, the locations here of the highest grade and lower grade ore bodies that might be mined in a porphyry copper deposit. It's always kind of made me think of a tooth in terms of its shape and its zoning. But the idea is that this shell is the ore shells just outside on the boundary between the potassic and the phyllic zones. Skarn deposits. Skarn deposits also really important. This is a metamorphic deposit. Meta meaning change and soma meaning body. So metasomatism changes the body of the rocks. Hydrothermal fluid moving that copper around. We do see sometimes that the igneous intrusion intrudes into carbonates, and so we get both a porphyry deposit and a skarn. Bingham Canyon is a good example of that. Sometimes with some associated lead and zinc mineralization. Big deposit up on the Gaspé Peninsula, closed in 1999, but I did see that Osisko Metals has been working on some updated resource estimates. Makes me wonder if the copper price is getting to the point, and last I saw it was $4.45 a pound. So maybe it's getting to the point where folks are wanting to reconsider the Gaspé Peninsula deposits. Antamina, Peru is the largest known skarn. It grades about 1.1%. It's 3,000 metric tons of copper. 15-year mine life on that one. Volcanogenic massive sulfides. These are hydrothermal fluids associated often with seafloor volcanism. We mobilize copper, zinc, and lead. And then when those fluids hit reduced sulfur in the near the seafloor, we get the black smoke. Those black smokers you've seen pictures of could potentially be VMS deposits in the process of forming. Deposition tends to be zoned. Copper tends to be deposited nearest the vent. And then as we get further from the vent, we go to zinc, lead, and iron sulfides. In a hypothetical world, it's not exactly how it works when you start having terrigenous sediment influences and some things go on there. There are a couple places you can have these, certainly mid-ocean ridges, but also when you have a subduction zone, the crust starts to get flexed, and that causes extension in the back arc side. And once you get that extension and thinning, you might have a shallow inland sea there and some hydrothermal black smoker style deposits there as well. 3 primary deposits based on magma type. We're not going to beat this horse too much. We'll talk about that in a minute. So here's your generalized diagram. You've got black smokers on the seafloor, copper deposition near the vent, followed by lead and zinc, and then out here at the edge, a little bit of iron. You may or may not have stock work as the fluids are coming up associated with this thin crustal zone. May or may not see copper stringers and some things down there. Better example here from the USGS. So we don't typically see VMS deposits associated with mantle plumes. The chemistry really isn't right. Here we have basically a spreading center, and you might see the formation of VMS deposits there. Here's the back arc over on this side. The continental lithospheres is being stretched, and we've got this shallow inland sea, some black smokers, and maybe potentially larger deposits there. And then there have been a couple of studies that show where we've got ocean-ocean subduction and we get island arc volcanism. We can get some small VMS deposits associated with those island arc volcanoes. We break them into 3 types. We name one for Cyprus that's mafic hosted. Typically they're copper rich. Bathurst district up in Newfoundland would be an example. We see Beshi type. These are back arc basin types. So that second type we looked at in the previous diagram where you get volcanic rocks with some siliciclastic influence. The Beshi deposit in Japan, and then one called the Windy Craggy deposit, which seems to me to be very descriptive. I want to go stand up there just to see what the weather's like and see if it really is windy and craggy up in British Columbia. And then finally the Kuroko type, which has some bimodal volcanism. That's where you have both mafic and felsic volcanism, and it really is characterized by some distinct zone mineralization. That's Kidd Creek up in Ontario. This is a fairly nondescript sample, but it was taken from Kidd Creek. I was fortunate enough to be in Kidd Creek in 2001, and this sample's been traveling with me now for 24 years. I think Maybe that's a lot of miles to haul a sample around. Sediment-hosted copper, really it's hydrothermal fluids encountering reducing conditions in sedimentary rocks. It could be because of the presence of organic matter. It could be because there's a redox zone. It could be because of the minerals themselves, right? Mostly these are in sandstones or siliciclastics, and you just have to have that reducing agent. It doesn't really matter what that reducing agent is. These things tend to be strata bound, meaning they're limited to just that strata that had the reducing agent, and they are epigenetic. If that's not a term you're familiar with, it means that they form significantly after the lithification of the rock. Those are two separate events. Fluid sources, hard to say, could be through sedimentary basins in response to some sort of tectonic event. And then they leach the copper from some source rock. It's often thought to be red beds, but it could also be volcanic rocks. Kupferschiefer is probably the most famous example. We've been mining that now for 800 years, and it has a tremendous lateral extent throughout Germany over into off into the east. And then the Central African Copper Belt, which is now the largest known sediment-hosted copper deposit. That's primarily in the border of the Democratic Republic of Congo and Zambia. This is the extent of the Kupferschiefer. This is the extent of the unit, noting that we see outcrops that's been mined in Belgium, Germany, over into Poland, and even into Lithuania. So a tremendous lateral extent, but it's not necessarily of economic value everywhere. Then the Central African Copper Belt, you can see in the inset here to give you an idea roughly where we are. And then the DRC right now with the most well-developed mining industry, although tremendous amounts of potential copper production both in Zambia and DRC. Finally, Mississippi Valley type deposits. We had a whole talk on those, so I'm not going to beat this horse much. Hosted in carbonates tend to be low temperature, hydrothermal brines that pass through basinal sediments. Most of the time they're zinc and lead rich, but every once in a while you see some that are copper rich. The Castile mine in the Viburnum Trend is a great example. The East Tennessee districts in the U.S. had, in some cases, 1.5% copper. And then Kipushi in the Democratic Republic of the Congo is an MVT, but the thought is that it maybe remobilized some copper from the Central African Copper Belt. All right, that's the background. And so now we're going to get into the meat and potatoes. And before we do, we need to talk about something called the mineralogical barrier. It was first put forward by a guy named B.F. Skinner up at Yale in 1976. He published a paper called A Second Iron Age of Head. And what he talked about was this idea that for geochemically scarce elements like copper, there will be an energy cost that has to be overcome if we move away from minerals that are fairly easy to process. If we have to start using things other than sulfides, oxides, and hydroxides and carbonates as ore minerals, if we have to start processing those silicates, the energy cost will be a barrier to production, and it will result in a rapid rise in copper prices once we use the known easy to process materials. And he sketched it out like this. So the blue line is for these geochemically scarce materials. We go from sulfides to carbonates to oxides, and then we get to where we have to utilize copper silicates, and the amount of energy we have to use is very large. So we end up using much more energy and creating a much more expensive cost. Geochemically abundant elements, it's a little easier. Minerals, it's easier, right? We don't have to go from mineral to mineral to mineral to mineral. Aluminum is a great example. It's 15% of the crust. We really like to get it out of hydroxides. We'd love to mine bauxite, but if we run out of bauxite, we could mine nepheline. And if we run out of nepheline, we could mine another cyanide. And if we run out of cyanides, we could mine granites. And if we run out of granites, we could mine clays. And if we needed to, we could mine the sidewalk and find aluminum. And each of those steps would be fairly small. There wouldn't be a really large energetic step. And that's going to potentially come into play in copper. So we want to be aware of the mineralogical barrier. This diagram shows copper production globally from 1900 to 2010. The numbers aren't the important part. The important part is the best fit line, because the best fit line shows that copper production has been increasing exponentially, right? Exponential increase reflects an exponential increase in demand, right? Because supply and demand are linked. There's another diagram showing the same thing. This is as of, again, 2010. We have an exponential increase. Their projection is exponential increase until about 2035. And then based on what they see, this is this research group, in terms of exploration and production, a decrease in copper production starting in about 2037, which would imply that if demand continues to increase, we should start to see a significant gap between demand and production by 2035. Let's look at it historically. The first time we produced globally 1 million tons of copper was 1912. To 1937, we produced 2 million. That's a doubling time of 25 years. We produced 4 million tons in 1961. That's a doubling time of 24. 8 million tons in 87. That's a doubling time of 26 years. 16 million tons in 2009. That's a doubling time of 22 years. We do the math, that's a doubling time of about 24 years, just over, which means that we would project that by 2033, we should be producing 32 million tons of copper annually. So we can use this number, a 24-year doubling time, to help us make some predictions. If we look at copper demand projections by folks like S&P Global or BHP or Rio Tinto, we get a pretty broad range. It ranges from 37 million tons per year demand on the really conservative end to closer to 65 million tons on the less conservative end. The number that you see most often when you read these projections is 50 million tons per year by 2050. That fits with our projections. That would put us with a doubling time of 24 years, producing 64 million tons by 2057. So if we can continue to enhance our copper production, we should be able to meet copper demand. That's a big if. That's a big if. Let's look at it another way. If we go to the entire 20th century, we use USGS numbers and we total up copper production, and I'm including the year 1900, even though it's the last year of the 19th century, so this is 1900 through 2000 inclusive. We produced 410 million tons of copper in that 101-year period globally. If we look at projected use for 2025 to 2050, the most conservative projections say we're going to need 1 billion tons. So in the next 25 years, we're going to need 2.5 times the amount of copper we produced in the entire 20th century. Put it another way, in all of human history through 2025, we've produced about 700 million tons of copper. We're going to need more copper in the next 25 years than has been produced in human history. So we face a challenge. And because copper is fundamental to modern society, I think you can argue clearly that copper is among the most critical of minerals. Now, the next little piece here is going to depend on talking about things like ore and exploration. And if you're not in that part of the industry, I'm going to give you a little vocabulary. And if you are, please remember this is 10,000 foot level and I'm not going in really deeply. Exploration, it's the process of finding a mineral deposit. That's all it is, by hook or by crook, using whatever analysis or processes that we need to use. We want to find places where minerals are concentrated. A mineral deposit is just a place where the minerals that occur at a higher concentration than background. It doesn't mean anything else. It just means, oh, look, there's more of mineral X here than normal. A mineral resource is a concentration of those minerals that has the potential for extraction. Doesn't mean that it can be extracted. It doesn't mean that it's been measured. It doesn't mean that it's been drilled or refined or defined. It just means that this one's good enough that when we look at it objectively, we think there's potential for extraction. Mineral reserves are the part where we can say we have done all of our due diligence. We know the concentration, we know the grade, we know the geometry. We can mine this economically and legally. Not only is it going to be mineable at a profit, but we have the permits in place, we've done the environmental work, and we can come in now and start extracting this material at a profit. The term reserves is very specific, and it has specific legal meanings. And it's important because reserves are made of ore. One of the most common mistakes that non-mining people make is they talk about ore deposits and mineral deposits as if they are the same thing, and they are not. For something to be ore, you have to be able to mine it at a profit. Ore has an economic definition. And if things change, copper price goes up, things that used to not be ore may become ore. If copper price goes down, ore may no longer be ore. So things can change, right? That and ore is not always something that's ore today may not be ore tomorrow. Likewise, if costs change, the price of diesel fuel goes from $3.75 a gallon to $4.25 a gallon, that can also mean that something that was ore today may not be ore tomorrow. So that's one of the most important distinctions that I think we can make is the difference between an ore deposit and a mineral deposit. Gang is just the waste stuff. It's what we throw away. And then I'm going to give you a couple of other things here that we probably won't talk about. A feasibility study and a pre-feasibility study. These are steps. You do pre-feasibility first and ask yourself technically, economically, and logistically, is a project viable? And if you determine that it is, then you go through the detailed technical steps and economic assessment to figure out how to bring that deposit online. So sorry I did that timeout, but I needed to do that because the next piece is all about exploration and discovery. Left side here is from S&P Global. And what this shows is over time, either the number of reserves or the number of new resources compared to exploration budget, which is the blue line. And what you can see here very clearly is the amount of reserves and new resources is decreasing and the exploration budget is going up. You can also see it over here on the right. If we look at the number of new discoveries, that number has decreased drastically, really starting in about 2014. But the amount of money being spent on exploration budgets is quite large. So what we're seeing here is increasing demand for copper and decreasing discovery. And there are a couple of reasons for that, right? The first reason is that it's hard to explore, it's hard to do greenfields exploration. And by greenfields, we mean exploring for minerals in places that haven't been developed. It takes exploration permits. You have all kinds of environmental reporting and compliance to do. It's necessary. I don't want it to sound like, I don't want to sound like I'm saying that it's not important. It is, right? We don't want to leave a big mess. But greenfield exploration requires more hoops, where if we go to places that have already been mined and we're trying to expand those places, that's brownfields exploration. It's a little easier to do that. Problem with brownfields exploration is in many, many cases, the really big high grade stuff has already been found, right? So we've got two processes occurring at once, but the net is we're spending more money on exploration and we're finding fewer resources. This shows up in the headlines. When we look at the headlines, May 21, prices go to records. Ivanhoe's Santa Cruz project to be operational in 2028, but we've got a copper crisis. Copper prices reflect structural deficits. We don't have the right structures in place to bring the commodity to market. We have major risks because we've got supply shortages that are looming. We've got refined copper markets for the first time seeing a supply deficit. And this was just in January 2025. So right now we're struggling as a global community to meet global copper demand. And that's because demand's going to change, right? Demand's changing. First off, if we look today, 89% of demand comes in four sectors, 70% from power generation and transmission, 7% related to the energy transition. And that would be things like bringing more wind turbines online, bringing more infrastructure in for solar generating plants, and even the copper resources that are necessary to bring on things like nuclear energy projects. AI and data storage now accounting for 1% of demand, and transportation being 11%. This would be electrification of cars, putting in infrastructure for electric trains, trams, public transportation, things of those nature. If we look at the projections by 2050, those four areas will account for 99% of demand. And the largest increases will be in the energy transition, data centers, tech and AI, and transportation, the electrification of our transportation grid. So what we're going to see is power generation is going to have to go up, but power generation is going to pale in comparison to some of these other applications. And it's complicated. There are some other factors out there that complicate our ability to meet global demand. One of them is that if we look at copper deposits that are currently being mined, according to BHP, that's the largest mining company, mining conglomerate in the world, the average copper grade since 1991 has decreased 40%. What that means is rich, high production mines are becoming fewer and fewer. And what we're having to do is mine larger and larger amounts of lower grade material. This decreases profit margins, increases environmental impacts. So one of the complicating factors is there are fewer high grade deposits online. Second is the role China is going to play. China is the largest copper consumer in the world. They consume about 20 pounds of copper, about 2.5 pounds of copper per person in China, and that number is only expected to increase as the middle class in China expands. They're also the world's largest refined copper producer, producing about 12 million tons a year. That's about 47% of global supply in 2023. I don't have that number for 2024-25 yet. And we know that China is a strong player in the geopolitical world, and that they have a history, as the Chinese government does, of using their position in the global marketplace to manipulate the market for their benefit. Chile is the world's largest copper producer. In 2024, they produced about 5.3 million tons of copper. That projected production is only expected to rise to about 5.4 million tons in 2034. So with the increase in copper production from the world's largest copper producer, looks like it could be nominal. Throw in Peru at 16% of global production and the Democratic Republic of Congo, DRC, at 17%, and you've got three countries that account for just almost 60% of global copper production. What was it Mark Twain said? He said, put all your eggs in one basket and watch that basket. And we kind of have all of our copper eggs in one basket, so we really need to be watching that basket. Now, the U.S., we could be a substantial player. We have substantial reserves, but there are a couple of problems for us. One is we don't have a lot of refining capacity. So even if we can make great copper concentrate, go to the Viburnum Trend, go to Doe Run, and they make a copper run, and we've got this really high-grade copper concentrate, it still has to be shipped somewhere to be processed. So our refining capacity is a problem. And then the other challenge for the U.S. is that the time from discovering a deposit to bringing it online as a producing mine can be as much as 30 years. Now, it's not that in every case, but take Resolution Copper down outside Phoenix as an example. They've been working on that mine since at least 2010. They're 15 years in. They're probably, I don't know the exact number, but the number I heard the other day was $800 billion in, and they're not producing concentrate yet. So that can become a challenge. And it's not just in the US, it's in Europe, it's in Australia. The regulatory environment, and rightly so, right? We don't want to make a big mess, but that environment can make it difficult. So what's the future hold? Well, look, Bloomberg NFH is a division of Bloomberg News. They say if we're going to meet copper demand, we're going to need industry to invest 2.1 trillion with a T dollars if we're going to meet that demand. International Energy Forum says, hey, if we need at least 35 new copper mines, and I will tell you right now, they're talking about really big mines. They're not talking about your 500,000 tons a year mine. They're talking about big ones. El Shaki, they did a global demand analysis, and they think that by 2050, the demand's going to outpace not only the known reserves, but what they call the reserve base. These are the things that haven't been proven to be reserves yet, but we're including in as resources that are not completely blocked out. Cathlas, Simon Wood, this was an interesting analysis. They say, look, we're going to need 3 billion tons in the next 25 years if we're going to maintain our goals of decarbonizing the economy, increasing the electrification of transportation, and having our developing nations continue to develop, building the middle class in India, building the middle class in China. 1 billion tons, that's the baseline to maintain today's status quo with no changes. So the numbers that we see potentially are very large. And their numbers say, hey, look, we're going to need 80 mines that produce 500,000 tons a year. So it's a kind of bleak picture, I think. But what does that really mean? Well, look, copper is the foundational material. Modern society doesn't progress without it. One of our options is to find substitutes. And I was at Home Depot the other day, and one of the things I saw is aluminum wire for your house. Is aluminum wiring. They were touting the benefits of aluminum wiring. Well, we're thinking about using aluminum wiring because copper is expensive. We're going to have to invest in exploration. And we're going to have to invest in exploration outside of brownfields. We can't limit ourselves to brownfield exploration, and that's going to be deeply unpopular in a lot of locations where there is the potential for copper deposits and copper production. We certainly have to expand current projects, but it's just not going to be sufficient to meet demand. We have to find new resources in previously unmined areas. I think we're going to struggle with copper demand outpacing supply, even if abandon's too strong a word, but even if green energy initiatives, those mileposts are delayed, and instead of a 2035 or 2050 timeframe, we push that back to 2070 or 2080. I'm not sure that copper demand will keep up. I think what this means is we're going to have to rethink the way our regulatory agencies go about permitting exploration and mining efforts. I'll give you one quick example and then we'll finish up. 4 years ago, I was at a meeting in Belgium, and the Irish were talking about how they have changed their permitting process without minimizing quality. And they did it by coming up with a streamlined and standardized review process so that each county in Ireland might follow the same review process rather than each individual county having their own standards and processes. In the US, it would be like Oregon and Missouri and Florida agreeing to the same overall process to standardize that nationwide so that exploration outfits know what they're going to be working with. It doesn't mean to limit the quality. And in fact, the Irish have reduced their timeline now to where you can have an exploration permit in as little as 4 months. And some of the other permits coming in as few as 4 years, where in the US now sometimes mining permits take a decade to put together. So I think of all the things we can do, having an agreement on how we're going to standardize the permit process without limiting that quality and opening ourselves up to environmental catastrophe is going to be one of the most important pieces. I will stop there. I've got an extensive works cited pages. I'm just going to kind of click through these quickly. I haven't checked to see if the quiz is in the chat. It is, so the quiz is available in the chat if you'd like to take it. And if you have questions, feel free to go ahead and drop those in the chat right now, and I'd be happy to try to answer them. I see a comment from Doug Bartlett. Doug has extensive experience and expertise in this area, and he makes a great point that I failed to mention, and he's absolutely right. Water will be also an issue because in many of our copper locations, the Southwest U.S. being one of them, the availability of water is a limiting factor. So excellent point, Doug. Thanks for bringing that up. Anyone else with questions? Harvey, I see Harvey's got a question. He said, would you say rather than limited supply, our issue will be high prices? And he goes on to note that high prices will stimulate substitution and production. Absolutely, Harvey. I think that's going to be one of the issues. It's one of the reasons I brought up the mineralogic barrier. When we get to that point where prices become problematic, the search for substitutes will be on in earnest. And so I do think that it will uh, drive some exploration, but it'll also drive some substitution. Someone else I noticed, I think this was who was this? Was uh, Charles. He says water is an issue for AI. Absolutely. In fact, one of the things we're seeing is because these big data centers require tremendous amounts of cooling, they take a lot of water. Yeah. Charles also notes aluminum wiring was very inferior to copper. That is true. There were problems with aluminum wiring in the past. I don't know if it's making a resurgence because the product is better, or if it's making a resurgence because it's enough of a difference in price that you can afford to just replace it every 15 years rather than having that copper wiring being in your home for the duration of the home. Other questions, if anybody has any. All right. Well, before you go, a couple of quick announcements. Oh, there's one more. What sort of reserves percentage is likely associated with federally uh, owned lands? That is a great question. And in all honesty, it's probably not as much in copper as you might think, because the big copper producing areas in New Mexico and Arizona are, well, they are associated, but not as often associated as in places like Nevada. And I think Nevada and Utah, with a higher percentage of federally owned lands, changes to the federal process uh, could open up exploration. One other here from Matt Shoemaker. Western USA's lawsuits. A mining company can receive its permits, but lawsuits can tie up the commencement of production for a decade or more. Um, Absolutely, I think um, the not in my backyard issue is prevalent in copper mining. I think it's prevalent in mining in general, and I think we as geologists, we sometimes get a bad rap because our job is to go find the material. We don't necessarily produce it. We find it, we put the plans in place to outline where it may, we build the ore deposit models. The engineers are the ones that then put together the production piece and then build the tailings piles and design all that. So, often we're associated with this really negative aspect when we're reacting to a societal demand, Matt, and the societal demand is I want my I want my electricity. I want my electric car. I want to be able to go to the grocery store and pick things up off well-lit shelves. And I want to be able to ride the train or public transportation, whatever that may be. And there's a disconnect. And we as geologists maybe need to address it in terms of finding that resource and utilizing it for a public good. And part of the questioning is the overall public good from public transportation, reduced carbon, whatever those things may be, how do we balance that public good with localized impact? And that's a discussion that we as geoscientists maybe could um, be better at having. Michael asks if we can get a copy of the presentation. Michael, you have my email. Send me an email. I'll send it to you personally. But we'll also make this available on our member site. So if you're an AIPG member, you can simply log in and it will be behind the member wall so that you can have it. How much does recycling of copper add to supply? About 13% of copper comes from scrap right now. That number can go up. And then the type of deposit is the Kennecott mine in Alaska. Oh my goodness, you're asking me about one I just don't know about, John. I don't know the answer to that. So if someone knows, could you drop in the chat which type of deposit Kennecott is? My brain's telling me that it was probably porphyry copper, but I don't know. That is outside my area of expertise. Okay, one last thing. I was going to announce this at the beginning. Next month, if you're an AIPG member, got two big things that are going to go on for members. One is the Lunch and Earn webinar. Next month, September 30th, will be free to all AIPG members as a thank you. September will be Member Appreciation Month. Second, if you're an AIPG member and you don't have your CPG yet and you're interested in applying, if you apply between September 1st and September 30th, we will waive the application fee for you to get that CPG. It's our way of saying thank you for all the support you give us as members of AIPG. All right, thanks everyone. We will see you on the 30th, I hope. If you have questions, please feel free to email me directly. We would love to have any of you come and give a talk as well. Bye.